Awesome. All right. Happy Friday. Thank you guys for coming to hang out with me today. My hope and plan is to have those tests from yesterday. I'm going to start grading them either this afternoon, if I can find some time, or certainly tonight. I want to get them done this weekend. So certainly, hopefully, by Monday's class, I will have some good news for you in terms of how well you did yesterday. So hopefully that went okay. Hopefully you found it relatively straightforward and that it went okay. So, but I do want to get a jump on chapter 5 so that even though you might not like experience chapter 5 in the full way that I would really like you to, like over a period of like 3 weeks or something, we might just do a quick overview here over the period of a week, maybe a week and a half. I want to get to calculus because that's what's going to come after chapter 5. I want to get down to that because that will be a little bit more brand new, but so is this stuff. What we're going to do in chapter 5 is different than we have seen so far with trig, because chapter 5 is all about analytical trig, doing things a little bit differently and trying to figure out shortcuts and faster ways and ways to manipulate trig functions so they look the way we want or just mess with them differently. And this is the kind of stuff that you'll see that will take practice. And so I've got some work that we'll work on together. You'll have some practice this weekend ahead of Monday's class. And then probably on Monday, I'll just give you time to try them. Again, once we go through the ones that you struggled with over the weekend and the ones that didn't make sense for the things that I talked about today, we'll see. What I'm going to do in this chapter is lean on a lot of the skills that you already have, but in a much larger way, I want to utilize all of the hard work that other people have done in trig to make our trig lives easier. So let's start chapter 5. And in chapter 5, almost always, I want you to have that trig cheat sheet out, ready to go, okay? I linked it, again, to the announcement for today, so you can just open up the PDF if you're sitting there, or if you have it printed out, that's cool too. I'm a really, really big fan of using that, and sometimes we have to, right, because we don't have this stuff memorized. That's 4 pages of formulas and identities and relationships and things that connect one trig function to another, or whatever the case may be. So open up that trig cheat sheet and open up your notes because I want to write some things down. With a really quick, brief overview of an idea or two in 5.1. I'm going to hold off on actually finishing 5.1 until Monday because there was something I was trying to figure out during second period that I just really didn't have down yet. I didn't want to jump the gun on it, but I figured it out in the last like half hour, thanks to Zyla from second period. She helped bridge a gap for me. She actually taught me something, which was cool. So I will teach that to you on Monday. So quick couple things in 5.1, and then we'll get to really the big first new thing, which is 5.2. So write some things down with me. Have that cheat sheet out nearby, ready to go. That's not very dark. 5.1 is what I want to look at first. I'm just going to peek at something on my laptop here. 5.1 starts to get us more comfortable with one of the pages on that trig cheat sheet. Okay, so have that out and get yourself onto page 2. Okay, the page that has all of the formulas and identities on them. Okay, I'm going to pull it out on my side. But if you're on page 2 of that trig cheat sheet, what you see, right, formulas and identities, is you've got this page full of equations, okay, where there's no numbers in. It's just all x's or thetas or alphas or betas or whatever they decide to use, okay? And what you are looking at on this page, especially the ones that are called identities, right? Like left-hand side, top 3 sections, tangent and cotangent identities, reciprocal identities, and Pythagorean identities, all these things we all know already, that are always true. Like that's what an identity is. Like 1 + 1 is 2. That's an identity. No matter what, 1 + 1 is always going to be 2. And you know, x plus 0 is x. Always true, right? It's called the additive identity. If you add 0 to anything, it doesn't change. Or 1 times x is x. It's a multiplicative identity, right? Doesn't matter what I have. If I multiply by 1, it just stays the same. And it's always true. And that's what I want you to think of when you think identities, right? Identities are things that are always true, like 1 + 1 is 2. And so what we have in those top 3 sections are identities that we can count on, that we can lean on, that we can use to do a few things. Solve equations that may be otherwise unsolvable. Rewrite expressions so that they're simpler or more complicated if that's what we want. Usually not. Usually I try to make things simpler. But we can do that by saying, oh, you know what? Tangent is sine over cosine. Okay, cool. And maybe that allows me to do something that maybe I couldn't otherwise do. Or hey, sine squared plus cosine squared is 1. It just is all the time, no matter what theta you pick. And I can use that to make things simpler. And that's what I want to kind of get to, is showing you how to do it in more of a like, let's solve some puzzles. Like I'm going to give you a little trig puzzle, and you're going to use some logic and some problem solving skills to like complete the puzzle. Not necessarily solving equations. We'll do that in 5.3. We'll actually solve some trig equations potentially. I'm actually less worried about that than I am about you being more comfortable a week from now than you are today with those top 3 sections and how you can use them, okay? And so what I want to show you first is how your basic algebra skills can translate to your trigonometric algebraic skills, okay? And so I want to kind of connect some old ideas to some new ones and show you how similar things can be when you're working through something like 5.1. And that section is called Using Trig Identities. I want to show you how you can use basic trig functions, okay? And again, I'm not going to be able to finish 5.1. I'm going to kind of leap to 5.2, and I'll come back to it. The thing that I just want to show you today is how your algebraic skills in factoring can be applied to trig, okay? That if you had something like, I don't know, call this number 1, I'm just going to make it up. Let's say you had x squared plus 5x plus 6, okay? And you wanted to, let's say, solve an equation z equal to 0, okay? All right, we can't solve that because you have different powers of x. And so what we know is that if things are factorable, then cool, I'll just factor it and that'll help me solve. Or I can use a quadratic formula. Okay, cool, maybe I'll do that and that'll help me solve. Let's factor, of course, if it's factorable. So I'm kind of thinking like, okay, what 2 numbers add up to 5 and multiply to 6? Right, whether you set up the diamond problem or you just think it, or however you factor, either on paper or in your head, right? 3 and 2 are going to be the numbers that do that. Old news, I know. Okay, so cool, x plus 3 times x plus 2 is how that would factor, which means we could split it apart, set this one equal to 0, set this one equal, set this one equal to 0, and get some answers, right? You don't have to write all that down because we know how to do that. What I want to show you is how similar trig equations that look like that, how similar we can solve them, okay? So that if instead of it being x squared, maybe it's a trig function of x being squared. So like instead of it just being x squared, like maybe it's like sine squared x instead. Okay, and remember where we put the exponent, right? Right in between your trig function and your variable. And instead of it being 5x, maybe it's 5 sine of x, kind of replacing your independent variable as just x. Instead of maybe it's a trig function. okay, plus 6 equals 0, right? Identical in every way except for that independent variable. Instead of it being x, maybe it's just sine of x, or maybe it's cosine of x, or maybe it's tangent of x, or maybe it's pick one, right? It doesn't matter. As long as they're the same, as long as it's sine and sine, or cosine and cosine, or tangent and tangent, I can really treat them the same way. But I can think about, okay, what two numbers do what I want, right? Add to 5 and multiply 6. Oh, 3 and 2 are those numbers. Well, that means that this quadratic right? It's a quadratic type function just with trig, can still have the plus 3 and the plus 2 in it. That part doesn't change. It's just that instead of x, it could be sine of x. And we could do the same thing, split it apart, set them both equal to 0, and solve them separately, right? That idea can be applied to trig functions as well. And so all of that pre-algebra, algebra 1, algebra 2, and even honors pre-calc knowledge that we've got when it comes to all of the ways to use algebra to make things easier, I want you to realize that those connections can be made from polynomials over to trig, okay? And that's really, really helpful because now if I've got all these skills that I can use, I'm gonna use them to make my life easier. And I could do the same thing with the quadratic formula, or I could factor, what if it was like 5x squared? If you got leading coefficients, with a factoring by grouping could work, or you could do the 2 by 2 square with the box. You could factor it that way. Or, and I'll show you this on Monday, I think there's an even nicer shortcut for factoring quadratics when you've got a leading coefficient bigger than 1 that maybe you've seen before, maybe you haven't. I want to show you that one. I think it's super neat and so fast if you know how to use it. So I'll show you that on Monday. But you see how those two are the same, basically, right? Those are the kind of connections I want you to see, right? And there's other ones we can do too. I'm going to erase some stuff. Like what if it was like the difference of squares? Like call this number 3. Like what if it was x squared minus 9, right? And maybe we just want to factor. Maybe it's not even an equation yet. Maybe it's just x squared minus 9. Well, hey, difference of squares is one of those things that I want to recognize and be able to factor. Okay, square root of the first one goes first, right? Square root of the second one goes second. One's a plus, one's a minus. Yay, x plus 3, x minus 3, done. All right, we've got that shortcut that we know we can lean on, count on to make our lives easier, to rewrite things so they look a certain way, okay? And I don't care what your difference of squares looks like, as long as you can recognize perfect squares, it's factorable, right? And so any even exponent for x is a perfect square, right? X squared is a perfect square, x to the 4th is a perfect square, x to the 6th is a perfect square, because just divide by 2, you're taking the square root. So if you had, I don't know, like x to the 4th minus 25, that's a perfect square, because this is even. Obviously, 25 is certainly a perfect square, right? Square root of the first one, x squared, goes first. Square root of the second one goes second, 5 and 5. One's a plus, one's a minus. I don't care what order you pick. It's factorable. And sometimes maybe we even keep going from there, and we can keep factoring. And that will allow us to solve equations that maybe we couldn't, or recognize structure in a way that otherwise we wouldn't be able to. And what you'll see as we work our way through February and March and April, recognizing structure is going to be so critical to allowing the calculus choice that you make in doing things the hard way or the easy way, because there's both. You can pick the easy way. And as long as you know those shortcuts, you can get them done, right? And so, all right, call it sine squared x minus tangent squared x. Those are both perfect squares. They're being subtracted. That means it's factorable. Square root of the first one can go first. Square root of the second one can go second. One's a plus, one's a minus, right? And being able to see how 3 and 5 are the same question with the same answer, just a different input, is so critical. You guys see that? Is that cool? Can you follow along with what I'm putting down? Okay, sweet. Now, you don't have to be perfect at this stuff yet. I want you to start recognizing certain things and getting more comfortable, okay? That's what 5.1 is trying to accomplish, getting you to look at that second page of that trig cheat sheet, the top 3 sections, and noticing things that are always true. That sine over cosine is tangent. And that tangent is sine over cosine. And you can go either way, depending on what you want. You know that sine squared plus cosine squared is 1. It's going to be really helpful in us making things simpler. Because, man, if I could have sine squared plus cosine squared and I can just replace it with the number 1, then I'm done. Okay, and that might make things look the way that I want. Okay, and that's what 5.2 gets us into, is trying to make things look the way that we want. Not necessarily to solve equations, but just practice manipulating expressions and saying, okay, I can replace this with that. Why? Because it's on my cheat sheet as one of my trig identities. And I've got these formulas that I can count on to interchange them in ways to make things look the way that I want. To go from having 2 trig functions down to just 1. Or from going from powers of 2 down to just powers of 1, because maybe that makes things simpler for me when I'm dealing with trig or the calculus of trig. Really, now what I'm trying to get you to get is a calculus kind of mindset, okay? So that's what I want to do, is I want to preview what 5.2 tries to get us comfortable with, which is going to take some time. Work on it today. You'll work on some stuff this weekend. You will struggle with it probably this weekend. You will struggle with it a little bit today. We will struggle with it on Monday. And that's what makes it great, right? If it was easy, everybody would do it. All right, the hard is what makes it great. And yes, I did just quote League of Their Own, which is an awesome baseball movie. You should check it out. So let's do it. 5.2. But you're going to see how much I am leaning on that trig cheat sheet. Okay, so 5.2. Okay, 5.1 was using trig identities, the ones that are given. 5.2 asks us to deal with more complicated trig identities that don't show up on that list and prove that they're true. That, hey, maybe we could make a page 5 and a page 6 and a page 7, or literally hundreds of pages of trig identities just using the ones that are already there. Okay, 5.2, verify trig identities. Now, we're not proving the ones that are already on there. Those have been proven. 1 plus 1 is 2. I know that already. I want to use that to figure out what 1 plus 2 is. You know what I mean? Like, that's what I want to kind of do. And so you don't have to write this down, but here's what I mean. Like, 1 plus 1 is 2. That's already true. Okay, if that's true, then prove to me that 1 plus 2 is 3. That's what I want to do. Well, 2 is 1 plus 1, right? So I could replace that like this. Oh, 1 plus 1 plus 1. Yeah, I know that that's 3. I can do that. Like things like that, which I know seems almost obsolete and kind of silly to prove that 1 plus 1 is 2 or that 1 plus 2 is 3. But what if it's not quite so easy to see? Or things that maybe we don't know for sure that are true, okay? And so here's what I want to do. I want to do a handful of these with you as much as I can before we get out of here at what, 55, right? Yeah, 11:15 to 11:55. So what I attached to today's announcement is just a collection of trig identities that we're going to try to verify. Equations that are not the same yet, but we're going to make them look the same by following a couple really good sets of strategies. Okay, so what I'm going to do kind of off on the side here is kind of give you a how-to on what we're trying to accomplish, and then give you a couple strategies that are good. Okay, so how to verify trig identities. Okay, that's what we're going to try to do, is how to verify trig identities, how to prove that an equation that's given to us is true, okay, all the time, no matter what. So not solving anything, I just want to make sure that they are the same, okay? And so go ahead and open up that homework 5.2a and look at something like number 1. And notice a couple things. Number 1, the first thing to notice is that your x's are not in parentheses. Okay? And I'm using x instead of theta. I could use whatever I want. That's the first thing to notice. The second thing to notice is that my inputs are not in parentheses. That is an informal way of just cleaning things up, so you're not parentheses all over the place. Okay. Of course, if that was like x plus pi over 2, right? If I was doing a phase shift or something like that, okay, fine. I would need parentheses around that because it's a phase shift. But sine of x, or sine of 2x, or sine of 5x, or cosine or tangent or whatever trig function you want, if it's just a monomial input, I don't need parentheses around. Okay, and so notice that. Okay, so when I write this down, what is it? Secant x cosine. Secant x. I don't put parentheses around, but you know that they're there. Cosine x, also no parentheses around that one. Okay. The other thing you want to notice is that there's no symbol between these two, so we know that they're connected by multiplication. Okay, that's given. Okay, so we try to do things neater by dropping some of those helpful but sometimes unnecessary symbols. Okay, and that's supposed to be equal to 1. They are telling us that that is true. Our job is to prove it by using one or more of that kind of collection of identities that's on that trig sheet. So here's my idea with what we're trying to do. If I want to prove to you that an equation is true, if I could make the left side and the right side literally identical, 1 equals 1, 5 equals 5, x equals x, sine of x equals sine of x, then I've proven it to you. That is my goal, is to make, that's my idea, make the left side and the right side identical by using trig identities. Okay. Now, the thing that I want to make sure that I avoid is kind of treating this like me solving an equation, which is normally when I would like move stuff from one side to the other. Right, I would add 1 to both sides, or divide by 3 on both sides, or square root of both sides. I don't want to do that. Do not move terms from one side to the other. I know I'm talking into the board, so sometimes it gets muffled. Do not move things around that equal sign. Imagine this brick wall along that equal sign that you cannot cross. Okay, you can do anything you want to the left side as long as it's true, as long as you're using an identity. You can do anything you want to the right side as long as you're using an identity. Okay, and what I want to try to do, my goal here, is to make things simpler. Usually that's a really good goal. I want to try to simplify one side, or maybe both sides, okay, separately. I don't want to add things to both sides, divide things on both sides, square things on both sides necessarily. I kind of want to deal with them separately and see where that takes me. So if I want to make things simpler, a really good place to start making things simpler is to work on one side only and picking the side that's more complicated. Because if I pick the complicated side and I try to make it simpler, then maybe I'll get there. Okay, I'm going to start I'm going to work on the complicated side and see what I can get. Okay, so I'm working with just the left side. I'm working with just that expression, and I want to use some trig identities to try to make them simpler. Okay, and when I say use them, I want to give you some strategies on how to do that. Okay, now these are not set in stone, and there's not an order to these strategies. Like I don't always try this first, and then try this second, and then try this next thing third. It depends on structure, depends on what I'm looking at. And you're going to find that you are going to start some of these problems one way, and it's going to be a dead end. And you're going to backtrack and try something else. It's like a maze. Sometimes you take a path that you think is good, and you end up at a dead end, and you have to backtrack, maybe all the way and start over, or maybe halfway and then take a new route, right? You're going to see that this is going to work on things in your brain that we have not done a lot with. Logic, problem solving, okay, which is just great outside of math, but super, super helpful, which is why I'm not going to number these strategies. I'm going to bullet them. You pick one based on some of your ideas, okay, and you see what happens. And one good one, when you look at a trig identity that's already given, if you see exponents, like sine squared, sine to the third, sine to the fourth. You've got identities that have powers in them, like the Pythagorean ones. Okay, you've got, sine squared plus cosine squared equals 1. Okay, it's okay, Lydia, no worries. And so if I've got powers that are bigger than 1, I might lean more on a Pythagorean identity to try to help me out. But if your exponents here don't appear to be bigger than 1, then that's not really a great way to go. So what I'm going to do is write this down. If your highest exponent is 1 everywhere, so it's just sine and cosine and secant and tangent, no tangent squareds or cosecant squareds or anything like that. One really good strategy that you could start with is to rewrite everything on one side, of course, okay? Because that's all I'm going to do is work on one side in terms of sine and cosine. Sine and cosine. Because tangent is sine over cosine. And secant is 1 over cosine. And cosecant is 1 over sine. And cotangent is cosine over sine. And sine is already sine, and cosine is already cosine, right? We've got these 6 trig functions that can all be written in terms of just sine, just cosine, or some combination. And so take a look at what we've got. Secant of x times cosine of x equals 1. The left side is the one that's more complicated. There's more going on there. There's more trig functions, and they're being multiplied together, right? When I say complicated, I mean busier, has more happening. There are more terms, there's bigger exponents, there's more trig functions, you've got fractions, you've got parentheses, whatever. It's the side that's got more going on, which for me is definitely the left side. So I'm not even going to touch the right side. And I'm going to hope that eventually I can make the left and the right side identical. Like 1 equals 1. That's the goal. X equals x. Sine of x equals sine of x, something like that. Okay, so take a look. What could we rewrite on that left-hand side to make everything in terms of just sine and cosine?
Secant should be 1 over cosine.
Good. That is now in terms of cosine or sine, right? Do I need to change this one? No, that's just cosine. So I will leave it. And so all I've done there is used an identity that's already proven to me, because on my trig cheat sheet I can use it to rewrite my function. And now instead of having 2 trig functions, I am down to 1. That is simpler. Okay, now what do you think we could do to keep working on that complicated side to make it even simpler? what do you see on the left side that we can do algebraically to make things simpler?
Multiply them together.
Okay, and so when you multiply them together, we get cosine of x over cosine of x. Because when you multiply fractions that have just monomials everywhere, you just multiply across the tops and multiply across the bottoms. What is cosine of x divided by cosine of x?
1.
Your left side is identical to your right side. Put a check mark next to it because you have just verified this identity. We made the left and right side identical. We did not move things from one side to the other. We simplified one side separately from the other by working on the complicated side first. That's a simple one, okay? We just had to make one change. We did a little bit of algebra. We simplified, and we got it to be what we wanted, okay? Okay, that gets you started. All right, let's do another one. I wish I had left a little bit more space. Can I erase that? That one's pretty simple. I'm gonna erase it. I'm gonna slide over a little bit so I can try to squeeze more than one on this board. I just wanna keep this idea up here. Okay, number 2. Tangent of x, cosecant x, tangent x, cosecant x. And I can just say it like that. I don't have to say times. I don't have to say of. Tangent x, cosecant x. You can just read it exactly as it's written because we're starting to now be more comfortable with trig, which means we can be a little bit more informal when we talk about it. Here we go. Same idea. Okay, I've got an equation that they are telling me is true. They said verify, prove. That means they know for sure that that's true. Our job is to prove it by making the left and right side identical. How do I do that? I don't move stuff around from one side to the other. I'm going to simplify one or both sides, but just separately by working on the complicated side first. Complicated side clearly is one that has more going on, which is the left. There's 2 different trig functions. They're being multiplied together. Okay, so what could be a good idea, since I don't have any exponents, is to rewrite things in terms of sine and cosine and see what happens. And I know that that uncertainty is probably driving some of you crazy right now. Like, give me step 1, step 2, step 3, step 4. Sorry, there isn't. We've got good strategies, and this is good for you to try to do different things. So let's work on it, okay? Left side only to start, and let's see what happens. Rewriting everything in terms of sine and cosine using those identities that we already know, like tangent is sine over cosine, sine of x over cosine x. Put the dot for multiplication if it's helpful. I like to. Cosecant x is 1 over sine of x. Again, I'm not going to touch the right side yet. Maybe I never will. Maybe I will. Who knows? We'll see what happens. So I have rewritten the side that I'm working on, right? Work with one side separately, right? Working on the complicated side by trying that strategy and seeing what happens. Okay, now that you've used an identity, see if that allows you to make things simpler. Is there anything you notice on the left-hand side that we can do?
Sine of x cancels out on top and bottom.
Then do it. Make it simpler by dividing things away that go together. And so what are we left with on that left-hand side? Well, one fraction, 1 over cosine x. Stick with the left side because it's a little more complicated. Why? Because it's a fraction. What is 1 over cosine x? What is that?
Secant.
Did it. I made the left and right side identical. How? By using a couple identities. I used the tangent one. I use the reciprocal one for cosecant. I use the reciprocal one for secant. And it just kind of flows one line to the next. I'm going to try something and see what happens and see what I can notice in a way to try to make things simpler. Okay, when you get there, put a little check mark next to it. So you've done it, you've verified it. QED if you want, even better. Okay, I'll try to squeeze this one in here because we only have 5 minutes left. So I want to try to get at least through this third one, but maybe the fourth one too. Okay, number 3. Cotangent squared x, that's where the squared goes, right? Minus cosecant squared x equals -1. They are telling me for sure that that's true. We just have to prove it. Okay, and the way to do that is to use the identities that are already there, the ones that are given to us on that trig cheat sheet. Here's the thing though, my highest exponent isn't 1. My highest exponent is 2. If you have, let's see, how should I say this? If your exponent is bigger than 1, let's just say that. Okay, if your exponent is larger than 1, okay? And I'm just going to say, try, because maybe it works, maybe it doesn't. Try a Pythagorean identity. And this works really well, of course, if your exponent is a 2, obviously. But maybe it's a 4, or a 6, or an 8, because that's a power of 2, right? Even exponents can be used in similar ways. Just like we saw that x to the 4th minus 25, right, was still a difference of squares. I can use that to my advantage. And so I look at what I've got. I know what I want to do. I want to make the left and right side the same. I'm not going to move anything around. So I'm not going to like add cosecant squared to both sides or anything like that. I want to just kind of simplify one side. And usually I will try to work on the complicated side and see what happens. Okay. And so I'm going to look at that cotangent squared, cosecant squared side and see if there's anything that I can use to help go from 2 trig functions down to 1, or find things that I can put together, or factor, or something to try to make things work. And since they are powers of 2, I'm going to lean on one of those Pythagorean identities that has either this one in it or this one. But usually, when they're dealing with given identities, usually it's both. You're going to see a sine squared and a cosine squared, and I'm going to use the first one. Or you're going to see a tangent squared and a secant squared in the same equation, and I'm going to use that one. Or like this one, look at that third Pythagorean identity. 1 plus cotangent squared is cosecant squared. Cotangent squared and cosecant squared in the same Pythagorean identity, in the same identity that I'm supposed to try to verify. And what I'm going to do is replace something in here using an identity. Just like we said, oh, I know tangent squared is sine over cosine. Tangent is sine over cosine. I can use that. I replaced one side of an identity with the other. All right, look at that first identity. Tangent is sine over cosine. I took the left side and replaced it with the right. Or vice versa, it doesn't matter which order you go in, because here we replaced the right side with the left to make things easier, simpler. And so look at that Pythagorean identity and look what's already isolated. Cosecant squared x. This, not with the negative, just what's inside there, is already isolated in that trig identity, which means I can replace what's inside here with the left side of that identity that's on that cheat sheet. I can replace cosecant squared with 1 plus cotangent squared. And yeah, now there's 3 terms, I see that, but how many total trig expressions am I dealing with? How many total trig functions? I had 2, now I'm down to 1. And that is simpler. And now I just try to put stuff together. So it's kind of like use an identity and then do some algebra. Use an identity, do some algebra. Use an identity, do some algebra, and see where it takes you, okay? All right, so here's me doing some algebra. I'm going to get rid of the parentheses. Okay, cotangent squared x minus 1 minus cotangent squared x equals -1. Here's a function, use an identity. Okay, do some algebra. Okay, now what can we do? Well, what's cotangent squared x minus cotangent squared x? Zero. What's left on the left? -1. Okay, so use your identities. They're already written for you, and you can use the right side and replace it with the left, or the left side and replace it with the right, or you can even move stuff around, right? You don't have to write this down, just look, and then you can go. Like if sine squared plus cosine squared is 1, that means that sine squared is 1 minus cosine squared, because I can take this and I can slide it over. Why? Because it's a given identity. I can manipulate the ones from the trig cheat sheet however I want. I can slide all that stuff around, right? Those are given to me. The ones that I'm trying to prove and verify, kind of that equal sign kind of acts as a brick wall for me that I don't want to pass over in case I do something wrong. Like I don't want to divide by x, like that could mean I'm dividing by 0 and that could screw stuff up. Or square rooting both sides. I don't want to do that because, oh geez, maybe I'm square rooting a negative and that could screw stuff up for me, okay? So there you go. There's that third one. Okay, and I will leave you with that. Okay, number 4 is a little bit different because it's got parentheses, but it's got that power of 2, right? You got that 1 minus cosine squared. Hey, you know, be a really good idea. And maybe you start with this one right now. Replace 1 minus cosine squared with sine squared, right? This is what was in the parentheses. This is simpler. Okay, but you had to kind of manipulate things in order to see that. This is not something that maybe you pick up right away, and that's okay. It's something you just saw 3 of them, okay? You have 4 through 8 to try your best, okay? If you get stuck, I don't want to hear about that Monday morning. If you get stuck right now, working through this right now, shoot me a message. You work on it tonight, and you're stuck on number 4, 5, 6, 7, or 8, or all of them. I don't know what to do. Help me. I want to help you this weekend, not on Monday. I want to walk in on Monday with you having all of these to the best of your ability done so that we can practice more. I want Monday to be a practice day trying to verify identities, not me working through the ones that are already on here. So reach out. I will give you some hints. I will give you some ideas. Hey, why don't you try this identity in this spot? See where that gets you, okay? So do your best. I know that you might not get all of them, but I want you to try all of them, and the ones you get stumped on, I want you to reach out, okay? So I can kind of push you to try, you know, take a path. Run to a dead end, fine, you can turn around and go back, okay? Questions about any of the things that I've talked about today? Okay, good. So this is not due until Sunday before midnight, so get it done whenever you have some time. You can knock it out right now as best you can, or you can work on it when you have some free time. But Monday we will come back and we will practice some 5.2 stuff, and that'll be the last day of trig identities, which means you might not have a perfect, wonderful understanding of them. That's okay. I just want you to see them and know they exist and have a couple of decent strategies on what to do from there. Okay? If you're good, I'm good, and I will see you on Monday. Have a wonderful weekend. If you have any questions, stick around, and I'm happy to walk you through anything and everything.
Thank you.
Thank you.
Bye.